going to walk you through one more problem about something that is launched at an angle for projectiles. This problem says a soccer ball is kicked at a speed of 30 meters per second at an angle of 40 degrees. The problem asks you to solve for the time in the air, the range, and the maximum height. So a little picture that would correspond to this would be the soccer ball starting on the ground, getting kicked up into the air, and then landing back on the ground. For this problem, the starting velocity of the soccer ball would be shown with this arrow right here, and the starting velocity would be 30 meters per second, but we'll notice that the angle right here is going to be 40 degrees. And so we're going to attack this problem of a projectile launched at an angle. When we're doing these problems, I would usually start off by saying, hey, this velocity is at an angle. I am going to solve for the components of the launch velocity. So I'm going to solve for the horizontal and vertical components of the launch velocity. And what that really means is break your velocity up into a triangle. So we have this 30 meters per second, that's our launch velocity. We have it at this angle right here of 40 degrees. And so none of that is in the x direction and none of that is in the y direction. We have to split it up into this triangle to figure out how much. So this would represent the velocity starting that's in the x direction. And then this would represent the starting velocity in the y direction. When we're showing our work to solve for these, we want to say, okay, it's the sign that's going to solve for this y velocity because this y velocity is opposite from the angle, and I know my hypotenuse. So you could write that the sine of your angle is equal to your starting y velocity over your starting velocity. Or you could rearrange that and say your starting y velocity is going to be solved for by taking your starting velocity times the sine of your angle. In the x direction, we're going to be solving for the x direction, which is adjacent to our hypotenuse. And so you could write the cosine of the angle is equal to v0x over v0. Or when you solve for the starting velocity in the x direction, it's solved for by v0 times the cosine of theta. You need to write that equation down before you plug your numbers into the. So now that we have written our equations to solve for our starting x and our starting y velocity, let's use them. So the starting x velocity is going to be solved for using 30 meters per second times the cosine of 40 degrees. I'll make sure my calculator is in degree mode, and I will type in 30 times the cosine of 40 and get 23 meters per second. And let's solve for that y velocity by plugging in 30 sine of 40 to solve for my v0y. And 30 times the sine of 40 is 19.3 meters per second. So now that I know the x and y components of my launch velocity, my next step to solving this problem is going to be to make an xy chart. When I make my xy chart to list my given information, I'm going to go ahead and put the things that I know to be true for this problem. Something I always know to be true is that my horizontal acceleration is 0 and my vertical acceleration is -10 or -9.8 meters per second squared. Then I've already solved for my starting velocity in the x of 23 meters per second. And I've solved for my starting velocity in the y direction, which was 19.3 meters per second. And it seems like the only information I know is those things, and I need to have 3 pieces of information to solve for my fourth, which would be anything that I'd want to know. But the answer is when something starts and ends at the same height, The trick is that your delta y is equal to 0. So I need to plug in that delta y is equal to 0. Now that I know 3 pieces of information in my y direction, I can use my y information to solve for time. So what is the time in the air? I'm going to use my y bulldozer, 1/2 ay t squared plus v starting y times t to solve. So 0 equals 1/2 of -10 times t squared plus 19.3 times t. And what we could do here, don't tell your math teacher, is we could do like a little bit of bad math in order to solve for our answer. And what I mean by that is this is the same thing as 0 equals -5t squared plus 19.3t. I'm going to add 5t squared to both sides. 5t squared equals 19.3t. Then I can just cancel out one of these t's. And when I divide both sides by 5, I get that t equals 19.3 divided by 5, or 3.86 seconds. So the time is 3.86 seconds. And the reason I solved for the time is because it's my link for this chart. My time in the y and my time in the x are the same. So the time it takes is 3.86 seconds. Once I know the time, now I can solve for my range. When I'm trying to use the time to solve for the range is just a fancy way of saying delta x. And so what I'm going to do now is I'm going to use the bulldozer again, but in the x direction. And so it's always the same equation that I'm using. It's just what do I plug in? In the x direction, the acceleration is 0. And so that turns out that my delta x just depends on my x velocity times my time. And my x velocity I've solved for of 23. And my time I've solved for of 3.86. And so the range, the distance that that soccer ball carries, is going to be 23 times 3.86, which is 88.8. Okay, now that we have solved for the range, the last thing that this problem asks us to solve for is to solve for the maximum height. To find the maximum height, we're trying to find this y displacement right here at the peak. And so my advice for solving for maximum height would be to make yourself a new chart when you're at this maximum value. So I'm going to make a new chart to solve for my maximum height. I call it y max. And so in the y direction, we know that even when you're at your peak, the acceleration in the y direction is still -10 meters per second squared. We also know that the starting y velocity hasn't changed any, and so it's still going to be 19.3 meters per second. And then at the top, there's actually an extra piece of hidden information that is only true when we are at the top, at the peak. That when we are at the maximum height only do we get to say that our y velocity is equal to 0. So I'm going to use that hidden variable, that y velocity is equal to 0 only when I'm at the top. Now I have 3 pieces of information, and I'm trying to solve for a fourth. The fourth piece I'm trying to solve for is delta y at the top, delta y max. And so when I have those variables, this equation to me just turns into the plow. I like to say v squared equals v starting squared plus 2 times a times my change in, I'm going to put y's next to all of these because I'm using my y information. So I'm going to say that my y velocity is 0 at the top, that my starting y velocity was 19.3, that my acceleration is -10 at the top, and that I'm trying to find my y displacement at the top. So I'm going to square 19.3 And I'm going to subtract that over. So I've got negative 372.5 is equal to negative 20 delta y. Now I'm going to divide both sides by negative 20. And I get that my delta y at the top, that maximum height, is going to be 372 divided by 20, which is 18.6. So that is the maximum height that the projectile ever reaches.